stop after 50 minutes, but they are having questions since 40 minutes.
When Neiman talked last time, he went for like an hour and a half, even before the questions. It was quite fun. Goddard started inching closer and closer to the podium, and finally started going up the stairs. And finally, Neiman got the message.
Well, Peter hadn't moved yet, so.
Mine will be like 20 minutes, so I think we're safe.
Sorry?
My talk will be like 20 minutes, so we're safe.
Okay, so talk was kind of so we've got Elena Fuchs today, and she's going to talk about why number theorists might care about network optimization.
Right. Okay, thanks. So I guess a lot of people should care about network optimization for different reasons. But the one specific thing I want to talk about today is something that both number theorists and people that care about network optimization might care about, and that's expander graphs and families of expander graphs. And so what are expander graphs? Well, in 5 words or less, they're very connected but sparse graphs. So what does this mean? Well, let me just write down some notation. So let's say X is a graph. V will be the set of vertices of that graph. And E will be the set of edges. I'll use that in a moment. And so what I mean by this very connected but sparse is that, so let's say you have this graph. Here's the vertices. It's got some edges in it. And if I want to take some chunk of the vertices, say half the vertices, and delete them, so to delete a chunk of the vertices, you have to cut a lot of edges. So in other words, any set of vertices here has a really large boundary, meaning that by boundary I mean the edges coming out of that set of vertices. Okay, and as far as network optimization goes, you can imagine, say, the vertices represent some phones or something like that, and the edges are wires connecting the phones. And in a good network, you want to be very connected in the sense that you can go from one phone to another phone in many different ways. However, you don't want to waste a lot of money and resources on the material to make the wires. So you somehow want to come up with a nice model for that. And expander graphs are a good model for that. Okay, so let me write up an actual definition of these things. So a family of expanders. So you have some family of graphs xi. And to each graph xi, there's something called the Cheeger constant, h of xi, which is the infimum taken over all subsets of the vertices of the graph of the following ratio. So you look at the number of all the edges going from A to B over the minimum size of A and B. Okay, so each of these graphs has some Cheeger constant, and what you want to say in order for them to make a family of expanders is that there is some epsilon greater than 0 such that h of xi is greater than or equal to epsilon for all of the graphs xi. Okay, and if you can put a number on this epsilon or some lower bound for this epsilon, then you can say something about, you can somehow measure the connectivity of the graphs. And that's very useful to know in all applications, but it's a pretty hard question. Okay, now before I go on to the application to number theory, I just want to say a couple things without writing them down. So expander graphs are very useful for many different people, not just number theorists. Very recently, there have been applications to geometry and knot theory, as well as there's applications in probability theory and computer science and error-correcting codes, which I think you've heard about before. And I don't pretend to know everything about all those applications, but if you're interested, a really beautiful paper to read about this is one by Huri, Lineal, and Widgerson from 2006. It's a survey about expander graphs, and they discuss a whole broad range of applications of these things. And more recently, you can also Google Alex Slobodsky's lecture notes for the joint meetings in 2011. He also wrote, his lecture notes also address all the many applications of expander graphs. Okay, and a couple of things about the history of expander graphs, which is also very interesting. I don't have much time to say too much about it, but essentially expander graphs were defined in the 70s by computer scientists, and at that point they were defined but not really believed to exist. So it took a while for people to actually become convinced that these things exist. And we've come a long way since then, because today we know that there's actually many families of expander graphs. And these families of expander graphs come from certain nice groups, and I'll talk about how they come up in a second. And all the people involved in showing that these families of graphs are expander graphs are, I mean, there's just a lot of people, so I'll try to name some of them. There was Bergan, Gambard, and Sarnak, and Peter Varju, Halfgott, Pieber Szabo, Brullier, Green, and Tau. Anyways, there's a whole big group of people that went into showing this. But I'll go ahead and move on to one concrete application in number theory. So that's the affine sieve. And this was developed by Bergan, Gambard, and Sarnak. The paper is published in 2009, but the results were circulating around long before then. And okay, so what is the general idea here? Well, you look at integer orbits of certain groups, gamma, say in GLNZ. And, okay, so let's maybe say, so these orbits are gamma V. And you want to somehow count prime points in these orbits. So count prime points in gamma V. Now by prime points, what I mean is we can sort of interpret in many different ways. You can say you want to count vectors, one of whose coordinates is prime, or perhaps you want to take some sort of integer valued polynomial on the orbit and see how often it takes on prime values. Or you can also replace the word prime by r almost prime, meaning that you'll allow it to have at most r prime factors. Okay, so that's the general problem. And so for example, I'll just write up completely. You might want to look at number of v. Maybe I'll write it x in gamma v, such that the norm of x is less than or equal to t. And here you have to be careful about what norm you use. I won't say too much about that. And say you have some polynomial f, and f of x is r almost prime for some r. Okay. All right, so the crucial thing you need from expanders in order to count this is the following. So let's say gamma is finitely generated with generating set S. Okay, and you look at Cayley graphs, gamma z mod pz, these are finite graphs with the generating set S. So what are these Cayley graphs? Well, the vertices are just elements of the group. And two vertices v and w are connected if you can go from v to w via one of your generators. Okay, so you have this infinite family of graphs coming from all the different primes p. And what you want to say is that this family, so this is for each prime p, this family is a family of expanders. And that's sort of the crucial input about expander graphs into the sieve. Okay. And so how does this sieve work? Well, I'll start by just talking about a sieve over Z, and then it generalizes pretty quickly. Okay, so let's say you have a polynomial over Z. So I'll try not to make this too technical, because talks about sieves tend to get quite technical very quickly. So let's say I have a polynomial f of x over Z. And I want to count the number of x less than or equal to t such that f of x is prime. Okay, well, this might be a stupid question if f of x happens to be, say, a product of two polynomials, because then f of x is always a product of at least two primes. So you can replace prime by r almost prime for some r that makes sense. So this would mean that you're going to allow at most r prime factors. Okay, so how do we go about doing this? Well, we consider a sequence an, which is going to be the number of x less than or equal to t such that f of x equals n. Okay, so then what is it that we want to count? Then this is just going to be equal to the sum over n prime of all the an's, right? Okay. So this is a little bit difficult to count, so we'll replace it by something easier. So we'll let pz be the product of all primes less than or equal to z. Okay, so this z, you don't really need to know much about it. You can say of what size it should be depending on your problem. But if you're interested, it's a small power of this big T that you have here. Okay, and now instead of looking at this, what I'll look at is I'll consider the sum over n relatively prime to pz of all the an's. So I'm looking at all the n's that have few small prime, or that don't have any small prime factors. And this is a fairly good approximation to this, is the idea. Okay, and how do we do this? Well, we sort of use a truncated inclusion-exclusion principle. We cross out all multiples of 2, and all multiples of 3, we'll add back in multiples of 6. We keep doing this. And the important thing to understand here is, what do these sums look like over arithmetic progressions? So for example, what I need is a result of this type. So if f of x is just x, then we know that the number of x less than or equal to t, maybe greater than or equal to 0, such that x is a mod q, well, this is just simply t over q plus big O of 1. Okay, so this is something that we want to be able to say in this scenario. So something about these kind of sets. And essentially, more generally what we want is we want to be able to say that the sum of an over n congruent to 0 mod d is equal to beta of d times t plus some remainder term. This beta of d is just some ratio between 0 and 1. So here, for example, beta of q is like 1 over q. It has to be multiplicative. And this remainder term should be small comparing to the main term. So in other words, we want to make sure that this is a good approximation to this sum. Okay. So I guess maybe I should leave this down. So this is what's happening over z, and it's sort of well understood. It's been studied for many years. So what happens if you go to this affine sieve situation? So this sieving over orbits. So here, for example, you might want to replace this basically by that. So you want to look at x and gamma v such that the norm of v is less than or equal to t, and f of x is prime, or are almost prime. Well, you do the exact same thing, basically. So you define an as the number of points in the orbit of norm less than or equal to t, such that f of x is equal to n. And you do all this, and then you come to this point, and you want to make sure that you can say something like this about sums of an in arithmetic progressions. And so there's 2 points here. One point is that you want to be able to approximate it by something like this. You want to find some multiplicative function here. And then the other thing is this remainder term. You want it to be small. And this is not going to be true in general when you sieve over the orbit of a group for the sort of norm that we end up taking here. So the key ingredient here is specifically this fact here. So basically, I mean, it's hard to explain why this is in 2 minutes, but you can think of it this way. You're looking at sums over of these ans for n congruent to 0 mod p, and sort of the thing that comes into play is something about these Cayley graphs of the group mod p. So, okay, so this is the crucial thing that gives us that the remainder term is small and allows us to make this approximation of this sum by this expression here. Okay. And what do you get as a result of the affine sieve? Well, so if you look at this number here, so let's call this star, you get that the star is going to be t to some power over log t to some other power, where these powers are sort of depend on the situation you're looking at on your group and also on the r that you chose here. Okay, and this just means that the star is less than or equal to c times this expression, and greater than or equal to 1 over c times that expression. Okay, and so I wanted to mention one example really quickly. There's lots of beautiful examples of problems which can be solved using the affine sieve. So one specific example which can be quickly described is that of Pythagorean triples. So if you look at primitive integer Pythagorean triples, by primitive I just mean the triple doesn't share okay, so you have A, B, and C, which are the sides of a right triangle, and you don't want A, B, and C to share some factor greater than 1. Okay, so these ABCs satisfy an equation, f of ABC equals a squared plus b squared minus c squared equals 0. Okay, And it turns out that if you look at the orbit of the orthogonal group fixing this quadratic form, actually the special orthogonal group, over Z, acting on your favorite Pythagorean triple 3, 4, 5, you'll get all the primitive integer Pythagorean triples. Okay, so here, basically, the set of Pythagorean triples is described as an orbit of a group. And this group is, you can describe it, it has 3 generators. And you can ask all sorts of questions. For example, you can ask about the primality of the area of such triangles. So specifically, you might ask for the number of A, B, C in your orbit. So let's call this group gamma, and this V. So in gamma V, such that the norm is less than T, and say the area AB over 2 has at most 6 prime factors. Okay, so 6 here is the number to take. Then what you get is that you can, basically you get exactly this here. So you'll get that the number of such triangles can be described like this, and you can compute specifically what the kappa prime and kappa should be, but I think that actually hasn't been done for the number 6 here. As far as I know, Alex Kuntarovich has done it if you replace 6 by 25 or something like that. But essentially you get a result of this nature. In addition, the other thing that you get is that this set is Zariski dense in the Zariski closure of the full orbit, gamma V. And you actually also get this not only for, by looking at, not only if you look at the whole orbit, in the whole orbit for triangles like this, but also if you look at triangles like this coming from certain subgroups of this gamma as well. Okay, so that's just one example, and there's lots of other really nice examples. For example, Apollonian circle packings, which I've talked about in the postdoc talk, but I think there's no more time, so I'll stop.